In this problem, we're going to be going over Kirchhoff's voltage law. And to do this, we are going to look at this diagram. We are also going to look at the table that provides us with the voltages that we're going to use to find this. So Kirchhoff's voltage law is similar to Kirchhoff's current law. There is some slight differences though. And for Kirchhoff's voltage law, which is what is focused on here, we are going to be looking at the voltages, and we are going to be looking at the direction of our resistance. This is important because we need to see which of our voltages are negative and which of them are positive. We're going to draw the current flowing through here. We can draw it either way. I like to start from the bottom left and go like this. And if we draw it the other way, we would just have to stay consistent with what our voltage drop and our current direction is. So that is our current direction. Now I'm going to draw our voltage drop. I'm indicating this with the blue arrow. And voltage drop is from the positive to the negative. And that's how it's going to look for all of these. The voltage drops from positive to the negative. If our voltage drop is in the same direction as our current, the result is going to be a positive. Otherwise, it is a negative. So Kirchhoff's voltage law, in its very basic sense, is just all of the voltages added up in a closed circuit equal to 0. So that means we are going to have our VS1 plus our V1 plus our V2, and this is all equal to 0. Now, if we didn't know the voltages, which we are given the voltages here, and we're going to focus on the experimental voltage, but if we weren't given these, we would use the voltage law where we have voltage is equal to I times R, or voltage is equal to current times resistance. And that will give us the voltage if we don't have the actual voltage values. Here, we're going to assume that we have the voltage values and we're given them in the table. So we're going to plug these values in. If we look at our VS1, we can see that the voltage drop right here is in the opposite direction of our current. And because of that, it's going to be a negative. So we are going to have a negative Vs of 1. Our Vs of 1 is 2 volts, so we're going to plug this in here. Now we are going to look at our V1 and V2. They're both in the same direction as our current, so we're going to add both of these. Our V1 is 499 millivolts, and then we're going to add to it our V2, which is 1.491 volts. And this is also equal to 0. Now, 1 milli is 10 to the negative cubed. So that means we're going to have to move our decimal 1, 2, 3 times right here. And now we can rewrite this, moving our negative 2 volts to the right side. That way we have all positive numbers. And this is going to be our answer. If we add both of these together, we're going to see that we get 2 volts. And our 2 volts is equal to our 2 volts. And so the power being distributed in the power, so this means the power being dissipated from our voltage, which is why it's negative, is the same as the power absorbed, which means that our Kirchhoff's voltage law satisfies this.